Good afternoon, everyone. Thank you for giving me the opportunity to present today. My name is Masahiro Kubota from Team Norikenpi. Today, I am excited to propose adaptive control algorithms that provide fast and accurate vehicle control for vehicles with various characteristics. I look forward to share my insight with you. Let's take a look at the agenda for today's presentation. First, we'll explain the importance of high-precision vehicle control in autonomous driving. Next, we'll look at MPC as a high-precision control method, MPC or model predictive control. After that, we'll examine modeling vehicles using driving data. Then we will go through simulation and simulation results. Finally, we will wrap up with conclusion, where I will summarize our key points. First, let me explain the importance of precise vehicle control. High precision vehicle control is important with respect to 3 points: safety, traffic rules, and comfort. Autonomous vehicles need to coexist safely with other vehicles, pedestrians, and bicycles without coming into contact with them. They must also obey same traffic rules as other vehicles. To operate autonomous vehicles in compliance with established stop lines and speed limits, they need to follow the planned trajectory closely. And for the comfort of the passengers, the vehicle must not vibrate significantly against the reference trajectory. To make it easy for anyone to develop autonomous vehicles, algorithms are needed to achieve high precision vehicle control for vehicles with various characteristics. In this case, I focused on MPC to achieve highly accurate vehicle control. MPC optimizes control inputs based on mathematical models that predict the future state of the system. I explain this with the help of a figure. Using the target trajectory and current state of the system. Current state of the control target. MPC seeks inputs that minimize the tracking errors. Then prediction model, which is a mathematical model of the control target, is used to predict the state of the system from the current state to some point in the future. Based on the predicted future state, an optimization problem is solved to compute the control inputs that will minimize the target trajectory tracking error. Only the first control input in the calculated control input profile is then input to the control system. By repeating this process each time, control with a small tracking error can be achieved. To perform MPC, a predictive model of the control system is required. The predictive model requires that the system be represented by a discrete time state space model as in equation 1. From the explanation of MPC on the previous slide, we can see this. In order to find the optimal control input that minimizes the tracking error, it is necessary to be able to accurately predict the future state of the vehicle. To accurately predict the future state of the vehicle, an accurate discrete time state space model of the vehicle is required. In the following section, I will explain the method used by MPC implemented in Autoware and the method I propose to obtain from driving data. Autoware approximates the vehicle model to a bicycle model, as shown in the figure 1, to derive a discrete time state space model. Autoware offers a choice of 3 different models, but we will discuss the bicycle kinematics model without the steering delay, because the simulation model we have prepared does not have a steering input delay. Assuming that the vehicle is approximated as a vehicle with only 2 wheels, as shown in figure 1, and that the vehicle's heading does not deviate significantly from the target heading, and that the steering angle is a minute, The lateral motion of the vehicle can be represented as a discrete time state space model as in equation 2. MPC using this bicycle model as a predictive model will be compared with MPC proposed in the following section as the MPC implemented in Autoware. However, there are several factors that are not taken into account in bicycle model. This includes the motion of a vehicle with more than three wheels, a pedal lag, a time constant, dead zones, black box software intervention, and tire stiffness, and so on. To rigorously take this into account, one would need to measure the stiffness of the components, contact the vehicle manufacturer, and ask them to tell us what is in the black box, and so on. But doing these things and building up a mathematical model takes a lot of time and money. Therefore, I propose to use driving data to identify the vehicle system and build a discrete time state space model. Modeling vehicles using driving data has the potential to provide fast and accurate modeling for vehicles with various characteristics. Here, I explain how to model a vehicle using driving data. First, a time series of driving data is prepared. Driving data includes inputs such as steering angle and acceleration at each time point, and states such as position and posture. The output model for the input is the ARCS model, and parameter estimation is performed using the least squares method. The ARCS model assumes that the output at a given point in time depends on past output values and past inputs. In general, the ARCS model is expressed in equation 3. In this case, the order is set to 1 for simplicity. The ARCS model can be transformed to a discrete time state space model by obtaining the parameters. In this way, a discrete time state space model of a vehicle can be constructed from driving data. In order to verify the performance of the MPC using the model identified by the system from driving data, a vehicle motion simulator that takes into account various elements of the vehicles is needed. A simulator using OSIM was considered because of its ease of integration with Autoware. OSIM approximates the vehicles to a bicycle model and simulates its motion. Since our goal was to model a vehicle containing many elements, we didn't use OSIM for this project. In this case, the vehicle body 3D of dual track was used. Vehicle body 3D of dual track can consider four-wheel model, lateral corner stiffness, and relaxation dynamics, air resistance, and so on. It can also be used in simulating a block diagram environment for model-based design. This is a block diagram of Simulink for obtaining driving data using vehicle body 3D of dual track. Vehicle body 3D of dual track is used in the center in the block diagram. The left dial controls the steering angle, and the bottom right saves the state and input at each time. The main simulation parameters are described in table 1. The driving data used for the system identification was for 110 seconds every 0.1 second. The vehicle model used is the same as the parameters used for a normal passenger car. There are many other simulation parameters, but they cannot be presented here, so we refer you to the Simulink model. Since the longitudinal and lateral motion of the vehicle are considered separately in this study, coordinate transformations are required sequentially so that the x-axis is always in the direction of the vehicle's travel. The 110-second driving dataset was cut into 1 second segment, and the coordinate coordinates were transformed with respect to the posture of the first driving data in each driving dataset. Finally, 110 driving datasets containing 10 driving data were created. Using this dataset, parameter estimation was performed on the ARCS model to construct a discrete time space model. The NPC using the bicycle model and the NPC using the model identified from the driving data were used to perform trajectory tracking control, and the trajectory tracking errors were compared. The parameters of the ARCS model were estimated from the driving data with the trajectory shown in figure 3 and transformed into discrete time state space model. The discrete time state model with bicycle model is as shown in equation 5, where that of the system identified vehicle from the driving data is as in equation 6. And we will compare the magnitude of the error in trajectory tracking using NPC with the bicycle model and NPC with model identified by driving data, respectively. The reference trajectory used in this study is the one shown in figure 4. Figure 5 and figure 6 shows the tracking error using a bicycle model and the model identified by driving data. The RMSE of NPC using the bicycle model was about 15 centimeter, and RMC of NPC using the model identified by driving data was 12 centimeters. Therefore, on the evaluation axis of RMSE, the NPC using the model identified by the system from driving data was superior. I would like to conclude with the summary. NPC using a model that was system identified from driving data allowed for more accurate vehicle control than NPC using a bicycle kinematics model. The simulator with the symbolic model and MATLAB code constructed in this study can be used to evaluate other system identification and control method. The simulator built using MATLAB and Simulink has been uploaded to this GitHub repository. Thank you for listening.